Once again, I welcome you to the UNU-INWEH public event, the Science Talk. For those of you joining us for the first time, you are welcome. We're glad that you can make it today. Thank you so much. I am your host, Professor Grace Oluwasonya. Before presenting our distinguished speaker, please note that there will be an interactive Q&A session at the end of the presentation. At this point, there will be room for comments, Q&A, and any other contributions you may have. Please type your questions or comments in the Q&A chat box, and we will pick them up from there afterwards. Thank you. The topic of today's talk is From Threats to Opportunity Towards Science-Informed Policy for Addressing Health Grant Challenges. I know it sounds a mouthful, but we'll be focusing on how we can use a science-informed policy to address this climate change or any of the hard grant challenges. So let's talk. Our presenter is Professor Tricia Stadnyk. Who is she? Professor Tricia is the professor and Canada Research Chair in Water Resources Management and Director Science to Action at the first UNU-INWEH at the University of Calgary in Canada here. She leads a transdisciplinary team in water supply and security, including operational prediction and forecasting water supply under changing climates, with a focus on science communication and the breeding of multiple and diverse knowledge systems, including indigenous ways of knowing. I really like that. Over the past decade, she has worked with government and industry on short-term operational flood and drought forecasting, guidance for peak flow assessments, and long-term hydrologic projections under climate change across Canada and the global pan-Arctic basins. It is my pleasure to introduce Professor Tricia, the beautiful Professor Tricia Stadnyk. Tricia, you're welcome. The floor is yours. Please take it on.
Thank you very much, Grace, and to the rest of UNU-INWEH for hosting me this morning. It's my honor to be here today. Before I begin the actual presentation, I would like to pay tribute to the knowledge and the wisdom that has protected the lands and the waters that I currently reside on for time immemorial. I come from a place right now known as Mohkinstsis, which is where the Elbow meets the Bow River. We know it today as the City of Calgary. This is Treaty 7 territory and home of the Blackfoot Confederacy, and also of the territory, Northwest Ancestral Lands of the Métis Districts 5 and 6. So the presentation today will be broken down as follows. First, I'm going to talk about some of the grand challenges and define what I mean by grand challenges for what I do around water resources and climate change. Then I'm going to address some of the knowledge gaps in the science area, including the inadequacy of the data that we have, the networks, as well as the approaches and the tools. Then I'll transition into the operations gap. So where are the uncertainties and how can we mobilize those uncertainties into reliability for improving the calculations that we have to do under climate change? Then I'll talk about closing the education gap, which includes part of my work with the Science to Action portfolio for the UNU Hub here at the University of Calgary. And I'll end with how we can bring this all together to find a path towards science-informed policy. So let me begin first by talking about what I mean by grand challenges and wicked problems here. The interconnectedness of the natural and physical world and environment, along with how we as humans alter the landscape and the subsequent socioeconomic impacts or fallout, like we're seeing after all these natural disasters, make this whole situation of climate change and particularly water resources projections very complex. This demands transdisciplinary approaches and a shift in the way in which our community functions and communicates in order to inspire sound science being adopted into future policy to look at climate change adaptation, which is a very critical need with where we're at. Wicked problems are unique because they don't really have a definitive formula. So as a modeler, my whole world is in mathematics and modeling. And specifically, how do I know when I find the optimal solution or the best solution? The problem with wicked problems and this transdisciplinarity aspect is there really is no one right answer. There are only good or bad or worse solutions, and each wicked problem is unique unto itself. I often tell my team that I've experienced many floods. I used to live in Winnipeg, Manitoba, where it flooded on an almost annual basis. No one flood is ever the same. The second challenge that we face is that of scale. Climate change starts global. It is generated by all of us at the global level, but it is very much a local problem. It is felt and experienced locally. This map was generated by the Swiss Agency for Development and Cooperation, along with INFRAS, which is an European Union Climate Risk Agency. They produce maps of risk indices that look by country at the associated risks of intersectoral areas such as climate, health, food, energy, and political stability or geopolitics. Even though climate change is generated locally, this map very clearly shows the regional impacts are very different depending on where you are. There is no one-size-fits-all response to climate change. And as diverse as these risks are, the other issue that is shown in the little circle on the right-hand side is that a single stimuli, such as a change in temperature, can generate a knock-on effect that stimulates changes in weather patterns, which changes drought, which can lead to wildfire, which can lead to health risks, which can lead to flooding, which can lead to socio-economic impacts. So there's this chain of dominoes that we really need to account for when we're considering climate impacts. And from an engineering design perspective, ultimately everything in our built world has a design behind it. And there's a few challenges that we face here. As an engineer, I do a lot of work with practitioners. First of all, the traditional methods that we rely on for, let's say, intensity, duration, frequency, or IDF curves, and probable maximum precipitation or probable maximum flooding and flood risk, those methods now lack validity under climate change. They're no longer holding true. The main reason for this has to do with the underlying assumption of IIDs, or independent and identically distributed. This means that really all the events have to be generated by the same cause. That's not the case. Starting in 2010, here in Canada, we shifted from predominantly snowmelt-driven flooding to snow and rain. And so those records need to be separated. And then we run into the problem of the 2T rule. The 2T rule says that if we want to do a design that lasts, let's say, 50 years, that's T, we need twice that in terms of the data record, which would be at least 100 years of record. Typically speaking, we do not have that, particularly in Canada, and particularly that upholds the IID rules. So this is a challenge. Overlaying on that is that the existing infrastructure that we have in Canada, the bridges, the culverts, the dikes that protect us from the flooding, they're no longer holding under climate change and climate-driven floods. What you're seeing here in the picture is a flood from the 2014 Assiniboine River, which was just upstream of the city of Winnipeg, and it was a complete failure of the dike system. The reason this happened is because the dikes were designed to account for frozen soil, where the soils were a lot stronger and could resist the penetration of the water. This particular flood was caused by a rainstorm that happened in July of 2014, and clearly you can see that the dikes failed. So our infrastructure is now failing because it was designed under different conditions. And third, but certainly not least, is looking at adaptation planning. The way in which we operate our infrastructure or control our water and manage our water now has to be a lot more variable for very large swings and extremes from flood to drought. Particularly when you're talking about flood to drought, you have an issue of, do you store the water to offset drought that could come later in the summer? Or do you release that water to prepare for an incoming flood? And that's not an easy question to answer if you're a water resources operator. So let's talk about drought for a second. In fact, protecting against drought and predicting drought is much tougher than predicting peak flows and flooding. Drought is what we call a creeping disaster. You're often in the middle of it before you even realize that it has begun. And just like wicked problems, it often doesn't have a finite stopping rule. In fact, unlike flooding, drought is caused by the intersection of both climate variability and climate change, a lack of rainfall, as well as the need or the demand for the water on the ground and conservation practices. If the conservation practices are lacking, the end result of the drought is much worse. It is also very widespread, as you can see from this image. Typically speaking, it covers more than just one city or area. In this case, the drought of 2024, this image was taken February 29th of 2024 from the North American Drought Monitor, shows that the drought conditions spread mostly across all of North America. And so that's a very high consequence event that affects not only water, but the food, water, energy nexus. And the severity of that was impacted by the fact that it not only affected water supply, but it also affected food and our sustenance and therefore our economy. Unfortunately, some of the work that my team has done shows that North America, and particularly the central Midwest of North America, is likely to be one of only a few hotspots globally in the future that is going to experience not only an increase in the severity of droughts, but also the duration of droughts. So this is something that we do have to plan for, and we do have to have tools that are adapted to be able to help us mitigate water management practices. So I also want us to look at the issue of cascading risk or overlapping disasters. I'm going to talk a little bit about the disaster that just happened here in Calgary, which was largely an infrastructure failure. So for those that don't know, on June 5th, 2024, our water main from the Bears Paw feeder water treatment plant in Calgary, which is one of only 2 treatment plants that feeds about 60% of the drinking water supply for the city of Calgary, failed. The catastrophic rupture meant that the Bears Paw water treatment plant, seen on the top right here, Bears Paw inflow, had to be shut down, and the city became entirely dependent on the Glenmore water treatment plant. These 2 plants reside on 2 different rivers. The Bears Paw resides on the Bow River. You see the diversion from the Bow River into the water treatment plant on the top hydrograph. And on the bottom one, you see the Glenmore water treatment plant diversion that resides on the Elbow River. You can see the effect of the June 15th rupture, where the Bears Paw diversion dropped because the Bears Paw water treatment plant was no longer operational. And all of a sudden there was a spike in the intake or diversion into the Glenmore water treatment plant. Similarly, once that plant, the Bears Paw rupture, the initial rupture, was repaired on July 2nd, you can see that water started to be diverted back into the Bears Paw plant, and subsequent drop in the Glenmore plant because it now needed repairs after supporting an entire city for 1 month for the drinking water supply. On August 26, we once again had to shut down the Bears plant. That's this final drop here, because they found and identified 23 more weak spots in this water main that feeds the city of Calgary, or 60% of the water supply. Where this becomes more than just an infrastructure failure is when we overlay this on a hydrograph upstream of the Elbow River. When the Bears Paw water treatment plant went offline, the city of Calgary was 100% dependent on the Elbow River. This is a hydrograph of the Elbow River just upstream of the diversion into the Glenmore water treatment plant. The disaster happened just after the beginning of June, and you can see what happened here. Flows were already on the rising limb, following a very long and very severe drought where we were actually below the lower quartile in the Elbow River for an extended period of time. Had this rupture happened even 1 month before when it did, we likely would not have had enough water supply in the Glenmore water treatment plant to feed the entire city of Calgary. And we would have all had to line up with little buckets of water in order to get water supply into our homes. So this is an intersecting risk between engineering, climate change, but also a socioeconomic problem in the sense that we failed to conserve water adequately as a city, and the cost of twinning this pipeline, which is the city of Calgary is so dependent on, is extremely prohibitive. Okay, I'm going to talk a little bit about the knowledge gap here in terms of the science. So first of all, over 80% of the Canadian landmass is actually undergauged relative to the World Meteorologic Organization standards. This isn't a failure of government, it's mostly cost. We're a very large country with a very low population. Streamflow measurement and observation is extremely costly. And what this graph here is showing on the screen is from some work I did in 2020 with a master's student to look at the average record length for Canada, which is about 50 years. If we overlay that on the fact that most of those gauges don't actually monitor extreme stream flow or what we call instantaneous peak flow, but they actually tend to monitor more annual extremes, then oftentimes the data that we're using and feeding into our models is under predicting the extreme flows by at least 10%. So that means our models are really being tuned to lower peak flows. And then the third aspect is overlaying that on the fact that our data networks are skewed by the way that they're developed. Most of the gauges cover regional or continental scales. The problem with that is that we're really missing the hydrologic process studies or the consequences or impacts of climate change. We're only seeing the shift in stream flow. We're not seeing shifts in the other processes that really eco-hydrology is dependent on. So this is a complicated figure, but what I wanted to show here, this is the Athabasca River Basin. The headwaters is at the bottom left, and the flow goes to the top right up here. Depending on where we look at in the basin, in terms of what the model sees as important, there's an emphasis on different processes. So at the headwaters of the Athabasca River Basin, we have a lot of glaciers. So as a result, the gray and the blue pieces of the pie, the snowmelt and the glacier, are extremely important to the model at this point in the basin. But as we continuously move downstream, which is to the top right, we see that the processes that the model sees and responds to during calibration change. They shift to almost 3/4 dominant with evaporation to a mix of evaporation, base flow, and soil water, depending on where we are. If we take an average of all the gauges in the basin, we end up with this top right corner, which is a different distribution than if we just look at one point in the basin. Laying over this, if we actually change the metrics that we tune our model to, comparing simulated streamflow to observed streamflow, then the figure on the left shows us that, once again, the processes that the model sees and responds to are very different. So if we look at something like log NSE, we get a much more dominant evaporation signal than if we calibrate to the slope of the flow duration curve. There's a lot more results in this paper, but the point is that the information that our models get is both time and scale dependent. And we have to take that into account when we're doing the modeling, particularly when we're looking at climate change impacts. So the value of tracer-aided approaches, this is my specialty, my area of research. On the top right, you see a figure of a typical hydrologic model. Different arrows represent different fluxes from the atmosphere onto the land and down into the ground and eventually into the river. If we look at this not only as water, but simulate both water and mass, that's what isotope tracers do, then we can not only provide more data for model calibration, but it tells us something about the changes in the individual fluxes. We can sample isotopes not only in the stream flow, but also wherever there happens to be an arrow. And that actually gives us direct process information feedback that we can use in our models. These processes are really what changes early in climate change and what we need to have a better idea of. On the left-hand side is an isotope space plot. So I'm plotting the change in mass of hydrogen on the y-axis and the change in mass of the oxygen molecule on the x-axis. What's important here are the different lines. The gray line in the background represents the precipitation, the flux-weighted average of all precipitation around the world. Any deviation down from that represents an evaporation signal. So by plotting these lines along with samples that we've collected, we can actually calibrate the model's evaporation signal, which is something that we just can't do with streamflow alone. That's really important from a climate change impact and water management point of view. So this, as it turns out, actually helps us to improve model outcomes. This is a Pareto front, which shows different ways of calibrating the model. On the x-axis is the calibration to the streamflow only, and on the y-axis is the calibration to the isotope. As expected, if we calibrate to streamflow only, we get very high KGE values of, or high KGE values of streamflow. And this means that the model's performing well in recreating streamflow. But you can follow this across and see that it means it's not actually doing that well with isotopes, which means we're getting the right answer, streamflow, but for the wrong reason. We're putting the water in the wrong spot, and the isotopes are telling us that. If we calibrate to both streamflow and isotopes, then we get the purple points. The top right corner is a trade-off between both streamflow accuracy and isotope accuracy. And this graph shows us we don't actually have to give up a lot in terms of streamflow accuracy, but we get a lot better result when we incorporate the isotope data. Moreover, the orange points are simulating what happens if we don't have streamflow, if it's an ungauged basin, but we do have isotope data, which does happen at a few catchments across Canada. Then it's not perfect. We don't get a great streamflow result, but it does give us feedback in terms of where and how the model is performing in those particular catchments. Okay, the question is, the million-dollar question, does this really matter? And the answer is it does. So what I'm showing here are flow frequencies. On the y-axis are the streamflows, the peak streamflow, and on the x-axis is the return period, or basically the size of the event and how important it is in terms of return period. So 10 represents 1 in every 10 years, 100 is 1 in every 100. The different colors represent the different ways of calibrating the model. The dark purple is flow only. That's your traditional hydrologic model. The other two represent incorporating tracer data in some way, shape, or form. And what we can see is when we incorporate tracer data, we do a much better job of capturing the historic observations that are shown on the top graph as the black points. The bottom one is what happens to these simulations when you project them out 100 years into the future. And you can see that there's actually a pretty big separation, particularly for the extreme flows, between the different types of model calibration. Of course, we don't have future data to validate that, but after we did this study, the flood of record happened in this particular basin. And it was in 2017, we got a flow magnitude that was much higher than anything we'd seen before. So we reran the model simulations and checked how well each model calibration performed. And it was only the model that was calibrated with the isotope tracers that came anywhere close to capturing the peak flow simulation. The model that was calibrated with flow only resided at less than half of the peak that we saw in 2017. So that tells us that certainly incorporating tracer data does a much better job. Okay, but that's all the modeling space. Some of you don't care about the modeling space as much as you might care about the eco-hydrology space. One of the things that we've done with these tracer-enabled models is we've looked at integrating across different biospheres. So this is some of the work that we did, coupling a hydrologic model to an ocean model for the Pan-Arctic basins. The freshwater coming off the entire Pan-Arctic Circle, 23 million square kilometers, draining into the Arctic Ocean. We took these climate change scenarios as well as the historic scenarios, and we looked at what the projected increases to Arctic Ocean runoff are expected for the future. And we saw about a 22% increase over the next 100 years of the water that's going to be entering the Arctic basin. Moreover, when we coupled that with a NEMO ocean model that simulates salinity and ocean circulation, we found that that change in freshwater was actually significant for the circulation patterns in the model. What the bottom right figure is showing with the different colors is the salinity depth averaged over the first 5 meters of ocean. The dark blue represents freshwater. The light white or pink represents salty water. It should be salty, but particularly draining from the Canadian or North American landmass, we see this distinct increase in freshwater input. That's significant because the freshwater is not only less salty and less dense, but it's also warmer. And so we're actually tracking the heat by tracing water temperature on the terrestrial models and looking at not only the temperature of the freshwater and how that impacts the Arctic Ocean and the sea ice breakup, but also how that impacts the river ice and the river ice formation. And what we're seeing is that an average increase of 1 to 2.5 degrees Celsius by 2070 is expected in the water temperature from the freshwater basins, but that will also have an effect on the river ice in terms of how quickly the river ice disappears. So we're seeing shorter ice on seasons, and we're seeing earlier breakup of sea ice as a result of this warmer water entering the Arctic Ocean. For the people of the North, winter is freedom. It's when they can transport themselves and their goods across the ice. And so this is having a distinct impact on their lives and their livelihoods, as well as their culture. So water balance is really the canary in the coal mine. It responds to climate change much earlier than streamflow. And by evaluating to streamflow only and not including tracers, we're missing the biggest and most important feedback, which is the impact and consequence of climate change on society, on culture, and on the total water availability. So we do a pretty good job of these first two, climate to hydrology, but where we're lacking is in looking at eco-hydrology and the impacts of the water resources change, as well as changes in temperature, pH, dissolved oxygen, and isotopes, and how the trickle-down effect to the socioeconomic impacts and eventually policy formation happens. So, for example, climate change ultimately affects human health and well-being, as well as the environment. And by not including the socioeconomics of decision-making, particularly the way in which we value Earth system benefits and wetlands and other aspects of the land, we are missing the actual kinds of decisions that science policy needs to rely on. So operationally, I like framing this around a quote that actually was from the Second World War. This is an excerpt from Kenneth Arrow, who was working on 1 month ahead weather forecasts during the Second World War for the troops. The quote reads, "The statisticians among us are subjected to these forecasts to verification, and they differed in no way from chance. The forecasters themselves were convinced and requested the forecast be discontinued." The reply from the commanding general read, "The commanding general is well aware that the forecasts are no good. However, he needs them for planning purposes." And I think this sums up the fact that something is better than nothing. So if we want to advance operational hydrologic prediction as a community, we need to collectively recognize that climate change is happening at the global scale, but these tools need to be scalable down to the local scale where the decisions and the policy are being made and being felt by the actual societies. So addressing climate change requires us to get used to uncertainty. This is something that we have to deal with better as an engineering and water resources community. On the top left focuses on the strengths of our community, the confidence and reliability that we have in our projections based on the knowledge that we have. And this allows us to assess with confidence and with a risk calculation. When paired with the bottom left, the opportunity, this is the uncertainty. We know that there are things that we can't control, but we add uncertainty, such as different climate change simulations, to try to account for that and to try to get a better idea of what the risk might be. On the right-hand side are the things that might destabilize us and be harmful to our modeling process. Our weaknesses are the risks that we assume from random variations that we know exist. We often in the engineering community handle this by adding a factor of safety. However, it's a one-size-fits-all, and in many cases, as we're seeing with climate change, it's no longer adequate. The bottom right is the worst one. This is our threat. The threat of the things that we don't know about, and therefore we don't look for, and we don't try to control for. These are the things that when we're making the final decisions, we are often completely unaware of. So there are ignorance or our blind spots. The goal is to turn those threats into opportunities by looking for them and by modeling in such a way that we are including the uncertainty and translating the risk into something that we can say defines what we know versus what we don't know, or the reliability. So if we take a look at that in a different sense, the bottom line here represents the lower limit of an uncertainty envelope around a mean model simulation or flood estimate for different return periods for different flows. The top one represents the upper limit of uncertainty. You can think of this envelope as different climate change simulations if this was a future projection. By taking a time slice through any particular risk level, we can actually turn the uncertainty into a PDF and therefore a CDF, statistically speaking, we can turn that into the reliability of a particular set of simulations or flood estimate. So instead of producing a single design flood for a risk level that a client has asked for, my argument is that we should be producing something similar to this, which is across a range of risk levels, you could have these different flood magnitudes. That is a much more adaptive way of designing in case the risk levels and the flood magnitudes are changing in the future, and therefore our design needs to change. The reason why this isn't currently done in practice is because there's a need for accessible tools to be able to distill this kind of complexity down into something that is interpretable and usable by the open practitioner community. And that's where we come to the idea of a community of practice. By creating standards that include benchmarks that give practitioners confidence in the simulations that they're going to do and an expected idea of best outcome, then we can facilitate guidance and workflows that they can follow in order to do this. And right now, this area is severely lacking in Canada. There is not a lot of guidance in the water community on how to incorporate climate change. Second of all, if we're going to support these communities, we need to make sure that what we produce as academics and scientists is findable, accessible, interoperable, and reproducible, or the FAIR principles of the scientific methods and data management. That means that we have to produce tools that they can use. Third, and last but not least, is to increase the accessibility. There's a difference between producing something and making it available and having it understandable. So communication here is super important, and making sure that these workflows are digestible by people that are non-experts for big data, cloud systems, and cloud computing. We need to make sure that we're focusing on communication with practitioners as well as communication with non-experts, such as the public and the clients, to make sure that they understand the outcomes and the risks. The last thing I wanted to talk about in terms of operations was the need for improved standards. I've been doing a lot of work within the engineering community in Canada to help improve what adaptive design means and what the benchmarks are for climate change. Engineers Canada in 2020 mandated that all engineers must design to take into account climate change. However, no guidance was produced in terms of how to do peak flow estimation that accounts for climate change. In the absence of those standards, oftentimes a factor of safety, i.e. increasing the historic peak flow by 20%, is applied. We've shown in many jurisdictions through many floods that have happened in recent years that this is just simply inadequate. So with the absence of engineering standards and guidelines, it's a little bit like the Wild West. This is the next area that we really need to focus on and help improve the policy, but also the legislation in terms of how communities are designing and to what design level. Okay. Last but not least, before I wrap up, I want to talk about closing the education gap. I've had the good fortune of being able to work with outreach through the University of Calgary United Nations University Hub, as well as the university community. And this has allowed me to talk to the public and realize just how wide the gap in public perception of our water, where it comes from, and the precariousness of the supply is. In Canada, growing up as a little girl, I was always told that we're water rich. We never have to worry about water scarcity, but this simply isn't true. We have to change this conversation and start realizing that our water supply, yes, is one of the best in the world and one of the cleanest, but that doesn't mean that it's infinite. So when we take a look at the value of sci-art, this is a way of connecting with people on the values and the things that matter the most to them. Living here in Alberta and being a climate change and water resources researcher, this is a super important point. I can't go in guns a-blazing talking about climate change. Instead, I have to find a conversation that's relevant and important to someone. The picture on the right is a climate scarf that one of my students knit for me, or crocheted for me, pardon me. I'm not a knitter, so I don't know the difference. And the point of this was she was able to broach a conversation with two elderly women in a coffee shop in Calgary because they saw her crocheting and took an interest in what she was doing and asked her what the different colors meant. By thinking about the fact that we have a responsibility to convey the science and the impact and the relevance of our field to a broader audience, then that opens up a different avenue for exploring our research. So the QR code on the bottom provides you some examples from some of the work that my team has been doing that include digital maps, but also our GitHub repository and data visualizations, all the way to different art exhibitions that we are featuring around the city and in different parts of the country in order to be able to have and broach a conversation around climate change. So that brings us to a path to science-informed policy. The goal is to acknowledge that currently our science is being held back. It's being held back by a lack of openness, a lack of diversity, and a lack of transdisciplinarity being incorporated into approaches. We tend to focus on just one thing at a time, either the environment or society and human response or economy. Instead, we need to produce tools that are capable of looking at all three and the knock-on effect that one has on another. Second of all, operations and the science community need to do a better job of finding new data networks and incorporating them, but also being open to new knowledge systems that incorporate different ways of knowing and different ways of understanding the changes that we're seeing. Operations has to also be able to think about different approaches for concluding uncertainty and how we might create that with accessible tools. Third, we need to look at diversity of policy and governance that supports knowledge mobilization and a focus on adaptation to mitigation, including different ways of valuing economic change, both benefit and cost, such as the blue-green economy. And lastly, by supporting EDI and our next generation STEMers, this is absolutely critical to achieving training that is transdisciplinarity, that focuses both on knowledge mobilization as well as knowledge translation to make sure that we are disseminating our information to broad audiences. Thank you very much for your attention, and I'm happy to take some questions.
Wow. Professor Tricia, let me first echo the excitement and accolade from one of the participants. It says, Tricia, you are a superstar. So
thank you.
So I echo that, it's just so spot on, So Nicholas is asking, could you go into the role developing countries play in all of this?
That is a fantastic question. In one of my policy roles or outreach roles, I do some work with the United Nations over with the International Atomic Energy Agency. And I have the good fortune of meeting and talking to many ministers from around the world, including mostly ministers from developing countries, where climate change, unfortunately, is hitting the hardest. And they have the least amount of resources to be able to tackle this change alone. And the reason why they attend these meetings and participate so wholeheartedly is because they really need the developed nations to help support the modeling and the science work that is needed to make decisions in the developing countries. So that is a really important role to play, is that we can't just do this alone. That's why many of my simulations focus on continental and global scales. And I specifically target regions that are considered data poor or resource poor. So my modeling focuses on the Pan-Arctic basin. I showed you some of those results today, but we also do the similar kind of modeling for the global south, and specifically looking at drought in Africa and how that's changing water resources and how it's changing the risk level, and then how we make decisions in the face of that risk level. So a lot of it is by helping to support the modeling in the background.
Okay, we'll take you up. We'll take a rain check on that, at some point. But now, back again, in terms of the science, during the presentation, I'm just wondering, what about the health and safety impact of the isotopes, the tracers that you use? Can you say something on that? Because one of the reasons why in hydrology, using tracers, to calculate stream flow and all that is not so popular, the health effect, around that, because you have to throw them in water, and things like that. So what do you have to say on that point? Knowing that you use that predominantly, to change the course of this.
Yeah, so I mean, two things have to happen. First of all, you have to have the data, the tracer data, to actually calibrate the model to, or to be able to compare to and use. Collecting that data isn't always cheap and accessible, and it's not always there. However, it is cost beneficial in comparison to long-term streamflow analysis if you have to choose between one or the other. And I'm not saying streamflow isn't needed, it absolutely is, but isotope collection or tracer data collection is often cheaper and easier to do in remote regions. So once we have that data, the uncertainty, it's really interesting. Adding the isotope data actually doesn't add any uncertainty because there's no additional parameters. The parameters are controlled by the hydrologic model itself. So that's already there, and all of that uncertainty is encompassed in the streamflow simulation uncertainty. The only thing the tracers do is make it harder to get a good model simulation. And that's because you're adding a different level of validation to the model. So instead of telling the model you have to meet one constraint, you're now telling the model you have to meet 3 constraints: streamflow, oxygenating, and deuterium. So the range of possible simulations that satisfy that to a certain level of threshold that's acceptable is actually much smaller than the range of just streamflow simulations that match that. And so that's the beauty of adding tracers to the model. Now, I showed isotope tracers. That's just one possible tracer. I want to make it clear, my team does isotope tracers, but we also do temperature, dissolved oxygen, and other tracers as well in the models. So you can use that data in a very similar fashion, or you can use all that data if you happen to have it.
Okay. I guess that makes a lot of sense. But I also want to comment very quickly on the fact that in hydrology, we've actually come a long way. In the 80s and 90s, the problem is engineers don't even when we design, they tend to forget that they're actually designing for humans, and it becomes a bit tricky. Excuse me, in water resources management, because sometimes it's like we just forgot that everybody is a water user. So whatever it is we design, at the end of the day, is going to be picked up by humans, and things like that. So I like the fact that we've come a long way, and we're now, we seems to now have a deep understanding of why we must always incorporate the human dimension or the socio-economic aspect, that surrounds the human dimension into any of our modeling. Okay. I need to take one more. Let's see. There's another question. One more question, if that's okay. How can we as civilians contribute to this challenge in addition to voting? I like that.
Well, couple of ways. First of all, you can become a part of the community and advocate for the same kinds of things. So just to further what you were saying, Grace, I agree with you 100%. The engineering community has come a long way in recognizing that we're no longer just engineering for the sake of building structures, but that those structures house people, that people depend on them, and that the risks with climate change 100% affect people. And of course, in Canada, we take an oath to protect public health and safety. Where we fall short at the moment is in having models that simulate that entire chain of reaction. So we do a good job of simulating the climate impacts on water, but then that full stop is where the water resources community ends and hands that information over to the structures community, who then does their own thing with that. And then the economic side does their own thing, and so on. We really need people that bridge uniquely this gap in knowledge between environment, society, and economics to be able to look at the full chain from beginning to end, to point out where the vulnerabilities are and where the overlap and knock-on effects are and where the opportunities are. And right now, within engineering education, we're not doing a great job of educating engineers on the economic side and the society side as much as we are doing on the math and science side. So I would like to see more of that integrated. and more learning around that and more incorporation of that into the predictions that we're doing. That is where climate change challenges lie. Adaptation requires us to understand the barriers to adaptation, which is all a social science.
Yeah, all is social science. I'll hold on. One of my colleagues wants to ask a question, Miriam.
Thank you so much. It's a fabulous presentation. And I really like that you featured Zaya art and the show your stripes. And that was really awesome. I wanted to go back to your point about how we need to do a better job of incorporating new knowledge systems. And I guess I'm wondering if you have any positive examples of incorporation of indigenous or traditional ways of knowing, or citizen science, or other sort of different types of knowledge systems.
I'm so glad that you picked up on that. I didn't have time to go into it in detail, but that's exactly what I was referring to. So the most challenging is, how do we take indigenous knowledge and incorporate that into traditional Western science? And by Western science approaches, I mean, for example, models. Models are quantitative. They work on numbers and they work on equations and coding. Indigenous knowledge is story-based. It's an oral history. It's not even written down in many cases. And what we face as a community, as a science community, is the challenge of, number one, having Indigenous knowledge accepted as equally as valid, which it 100% is if used and interpreted in the correct ways and validated within that community in the correct ways. Again, this requires us to bridge the gap of how do we have hardcore modelers understanding Indigenous knowledge and Indigenous science, which is largely a social science structure as well. So an example of a project that I've been working on with Dr. Carrie Black for a First Nations community that has been differentially flooded, disproportionately flooded as a result of climate change because they're in a very low-lying area. We've done the traditional modeling, climate into hydrology, hydrology into hydraulic modeling to look at floodplain mapping, but we didn't have a lot of data and we couldn't really test if the model was accurate or not. So on the second side of the project, we have been doing community consultation, talking to elders and the community to understand time periods where significant community events happened, cultural events where they erected their teepees, to give us a sense for what areas of the land were dry on what dates, and then going back to check the model to see if the model is in fact simulating that on those same particular dates. And there's a whole host of other ways that we're incorporating the Indigenous knowledge into validating the flood map.
Okay. Are you good?
Yeah.
Okay. Manzo?
Yeah, I'm good.
Oh, okay. All right. Let me pick you up on this. On the public outreach, I want to say that's one of the reasons why the UNU-INWEH Science Talk was actually set up, because we have tremendous, amount, it's the level of work, scientists, researchers, we are doing, it's so massive. But it seems on the other end, people don't even appreciate the fact that scientists are busy, spending sleepless nights, day and night. Actually, I've been, asking for how we can have 36 hours a day, because 24 hours a day doesn't seem to cut it anymore. So a lot of work is being done, but at the end of the day, we're not really doing so much, at communicating, to the public. And we're also part of the public, I understand, but the majority, where the impact, is really felt. So what is your experience in this regard? I know you tried to share one example with us where you're, a student, but can you please shed more light on that part, because I think it's so critical.
Yeah, it's very important, right? So you're absolutely right that we are part of the community as well. And I'm not suggesting that we are above or separate from the community. However, by being immersed in the science and the language and the lingo and the jargon every day, our knowledge is different and the language we speak is different. And if we go into a public setting speaking like that, it can be very off-putting or offsetting to the public interest. So I am an engineer by trade and training. My undergraduate and my PhD were in environmental engineering. I spent 12 years in an engineering faculty at the University of Manitoba. And then I got to the point in my career where I was looking at water resource problems under climate change, and I realized this isn't a science problem. This isn't an engineering problem as much as it is a social sciences problem. My career had not prepared me for that. My training, I had not done social sciences training. So I decided to leave the engineering profession, and I went to a faculty of arts for 6 years in order to work solely with social scientists to try to better understand the barriers to uptake of change and the barriers to the conversation of climate change. I spent 6 years in the Faculty of Arts, and now just this last year, I've switched back to engineering, but maintained cross appointment with the Faculty of Arts. So having that knowledge on the social sciences side, understanding the psychology of freeze, fight, or flight, and the resistance to information is super critical for engineers to have. We have to change the way in which we have those conversations. That's part of what we do. We also make experiences that are more immersive and tactile, such as art exhibitions. We just recently, as a team, published a book of short stories that are written about our research, but are designed to highlight our research in a friendly and approachable way from our own personal experiences. We also do the technical side. We take the data that we produce from the models, but we make pretty maps and figures that synthesize information from both environmental change and socioeconomics together so people can see it as a one-stop shop. So there are many examples. The QR code that's on the screen takes you to some of those, but our website links you to more. So yeah, it's really not a one size fits all, but a multi-pronged solution. And mostly it's just about having conversations with people and making sure that you're getting the information out there.
Yeah, thank you for that. So, and I'll quote you, we have the responsibility to convey science. I guess that's one of the things I'll take away from today, because we have, you couldn't have said it better. We have the responsibility to convey science, but one more thing. You also talked about diversity of policy and governance.
Yes.
Now, let's just suppose that with the majority world, where most of the impact of climate change, all these grand changes are felt, had the unique problem of lack of data, lack of resources, and also how diversified can we be in terms of policy and governance on these issues?
Yeah. So there's kind of two sides to the diversity aspect. The diversity of policy means that we're looking at it from a transdisciplinary lens, but it also means that the people that are in charge of making the policy are diverse in and of themselves.
Yeah.
Enough with the one-stop shop. We absolutely miss things when we don't have all the best minds at the table. And all the best minds does not mean all the people with the same kind of training, the same kind of background, the same kind of look, the same kind of conversation. We have to diversify the table if we're going to stop missing things. And an example that I love to give my class is that up until the mid-1970s, there wasn't a single engineering building in Canada that was built with a female washroom. That wasn't a discrimination against women intentionally. That was literally that the people that were in charge of building the buildings and making the decisions never actually thought there might be female students.
Mm-hmm. Yeah. Welcome to the real world. I can take that just a bit further. Even the default design had always been masculine. I'm not saying it's intentional, it could be strategic, but, who knows, and the scary thing is now that we're fast moving into the AI world, the default design is also still masculine. And
exactly.
We're missing, and this is what we control the next, 50 years, of our lives. If you don't do anything about, if you don't do something about it now, we'll still have the same problem, 50 years down the line, because really the default design is still masculine.
Agreed. Agreed. And we've seen this with crash test dummies. We've seen this with design and buildings. We see this also with accessibility challenges around environmental disaster. And so one of the projects that I'm embarking on is working with a specialist in the social sciences to look at how people with disability can be evacuated and warned in due time in order to escape floods or severe disasters. So this is really what I mean by having diversification of policy so that we don't miss the critical gaps.
Thank you,
You're
Tricia.
welcome.
Thank you. I just don't want to be triggered to keep going on this, diversity kind of thing. But I guess we'll let it to rest at this point. We've done a massive, fantastic job. Today we enjoy this. I enjoy this, and I believe all our participants out there, you've learned one or two things. You enjoy this, and I'm sure. Very quickly, if you put an advert out, you're going to have, many more people jumping on board your transdisciplinary team, in this regard. So, Professor Tricia, thanks so much for your time and for the insights provided. We are so happy to have you. Thank you so much. And to all our participants, yes, you want to say something?
No, I was just going to say it's my pleasure. Thank you very much for hosting me.
Yeah, and to all who have participated in today's science talk, we appreciate your presence. Thank you so much, and we look forward to having you next week. Thank you, everyone. Take care. Bye for now. Thank you.